Okay, welcome to Lab 5, Intro to Stochastic Models. Now, we've spent several weeks now going over age-structured population models, matrix population models. We're going to switch gears right now, and we're going to have a chance to practice with stochastic simulation models. Essentially, what we're doing here is we are embracing the uncertainty that we always have about parameter values and about what the future might bring in terms of good years, bad years, who's going to live, who's going to die. We're going to embrace all of the different types of uncertainty in our models. And as applied population ecologists, that is what we need to do. We have to acknowledge that the uncertainty is there. And if we're going to make our models useful, if we're going to convince managers that our models are to be trusted, that our results are to be trusted, then we need to acknowledge that there is a lot of uncertainty in these systems that we're working with and in the parameter values themselves. So we've talked about in the last lecture, we talked about three different types of uncertainty that we need to account for in our models. The first one is parameter uncertainty, or just basic lack of knowledge, and we can represent this type of uncertainty oftentimes with just a lower and upper bound, like this birth rate, per capita birth rate could be as low as 1.1, could be as high as 1.9. We also sometimes see it as using this plus or minus symbol. We can say here's a mean per capita birth rate, and plus or minus 0.4 might represent a standard error around that mean value. And how we see it, this is how we may see it in the literature. We'll see that this birth rate has a confidence interval essentially from 1.1 to 1.9, or we'll see it as it has a mean value and a standard error or some sort of variance around it. And that can influence how we end up incorporating it into our analyses. Either way, the way we deal with this type of uncertainty is called uncertainty analysis. So the simplest way to do this is just to run the model for the lower bound and an upper bound and just enclose everything in the middle. The lower and upper bound kind of define an envelope of possible future values of the system, say abundance. And we can just run the model both ways. And we'll go over another way to do it in this lab as well. So the second type of uncertainty is just what we call demographic stochasticity. And we, even given that we know what the per capita vital rates are, that we know the probability of dying, we know the per capita rate of offspring production, even so, we don't necessarily know how to predict who's going to live, who's going to die, and how many offspring are going to be produced by each female. So that's called demographic stochasticity, and the way we deal with that is to use stochastic random number generators. For births, we use the total births. We use a Poisson distribution, which has some nice features for modeling births, and that is it produces whole numbers. We don't like fractional individuals, and it doesn't produce negative numbers because it wouldn't make sense. So we use you can read this as the total number of births entering the population is distributed as a Poisson distribution with a mean of total abundance times the per capita birth rate. So we can imagine a population size of 100 and a per capita birth rate of exactly 0.8. So to get the mean expected number of births, we just have to multiply 100 times 0.8. So the mean total births entering the population this year should be around 80. But we can't predict exactly. So it could be around 80. That's where the peak of this distribution is. But it could be even greater than there are females in the population. So it could be above 100 births. It could be on the other extreme as low as around 50 births. But in general, you would expect around 80 births. So that's what the Poisson distribution produces. To model the total deaths in the population every year, we can use a binomial distribution. And every time you see the term binomial distribution, you should think coin flipping. So it basically is a distribution that can be thought of as counting up the total number of heads out of a total number of coin flips. And here we're modeling the total deaths as a binomial distribution, a binomially distributed random variable with the total size of the population, which is basically representing the number of coin flips, and the probability of dying is equal to the per capita death rate. So we can imagine a population size of 100 and a per capita death rate of 0.2, and we can look at the binomially distributed number of deaths that we might expect. Now, the expected number that we would think that if we have 100 individuals and a per capita death rate of 20%, then we'd get 20 approximately number of deaths. But we can't predict exactly, so it could be under this binomial distribution, it could be as high as 30 or even above 30. And on the other extreme, could be as low as under 10. So this is demographic stochasticity. We just can't predict who's going to live, who's going to die. And finally, the third type of uncertainty that we have to deal with in our models is environmental stochasticity. And that's kind of luckiness or unluckiness at a population level. So that per capita vital rate might change from year to year just because the environment is more favorable one year and less favorable another year. This is environmental stochasticity. Now, we sometimes think of extreme environmental events, as being either catastrophes or, on the other hand, the term bonanza is sometimes used to describe an especially good, favorable year. And so that really catastrophes, which would be like droughts or floods, something really negative to the population, or bonanzas, are just another form of environmental stochasticity. So that's when a population gets lucky or unlucky, or very unlucky in the case of a catastrophe, or super lucky in terms of a bonanza. So in general, to model environmental stochasticity, we'll make the per capita vital rates drawn from random number generators. And we'll use something like either a normal distribution or another continuous distribution like a log normal or uniform distribution to represent the per capita vital rates changing but year to year. So we can imagine annual per capita birth rates varying between 0.8 and 1.7. And let's say that there's an equal chance that the value of the per capita birth could be anywhere between 0.8 and 1.7. We don't really know. We could use a uniform distribution potentially to model this. That's what it looks like. So every value between 0.8 and 1.7 in this case is equally probable. So of all these possibilities, they're all about equally probable. This is what the random number generator will produce. Or we might see that the mean per capita birth rate is around 1.1, and you might see that there's a standard deviation of 0.4. So the average year is birth rate of 1.1, but on the extreme values, you might see something about 0.8 or 2 standard deviations higher than that. So that would be 1.9 or even higher on an extreme good, favorable year, and could be down close to 0, basically, in a really bad year. So, and you see in this case, it goes negative because a normal distribution can go negative. So that's a little bit unrealistic to think that annual birth rate could go negative. So in that case, we might want to use a log normal distribution, which can't go negative. But in this case, we're going to let that slide, and we'll use a normal distribution. In general, we use a normal distribution or log normal if we want random numbers to have a central tendency. That is, there's kind of average values that are more common than extreme values. All right, and I'll pick up with one more demonstration in the next video.